and a colloquium we're going to have the remaining of the season, which I promise is going to be fantastic. And it's an immense pleasure that Professor Samuel Ting has joined us today. In fact, Sam has been here for a few days already, and remarkably giving a lecture yesterday and meeting with the students already yesterday. So this is also a sign of an engaged person in science. Right? So this is really something we love. I only have a few things to say about Professor Samuel Ting. Sam was born in the US, in Ann Arbor, Michigan. Then he left US for a while and returned. I'll make life short, but it's very, very interesting. So please, I urge you to look at his life story. It's really exciting. So you have no excuses not to do the same and to do more. So he was invited to attend the University of Michigan, where he received his bachelor and later on his doctorate in physics. And in '63, he joined the European, at the time called European Organization for Nuclear Research, CERN. In '65, he was professor at Columbia University, and he also worked at the same time at the Deutsche Elektron Synchrotron, also as DAISY laboratory in Germany, which is in Hamburg, close to us. Actually, now there are two DAISY, one in Hamburg and one in Zoid. In '69, Sam became professor at MIT in the States. Now, why did he get the Nobel Prize? He received a Nobel Prize in '76 for the discovery of the J-psi particle. Do you know what that is? You should know. So the J-psi particle is a meson, is an hadronic state made of a charm, anti-charm quark. So even though it's for the discovery of the J-psi particle, the true discovery lies beneath, which is actually having discovered the fourth fundamental quark. Right? We have a fancy name for that. One is called charm. And that he actually charmed us with it. After that came beauty and truth. So he received, together with Burton Richter, the Nobel Prize, and Burton was at the time at the Stanford Linear Accelerator Center in US, and they received it for the pioneering work in the discovery of a heavy elementary particle of a new kind. I can only add that without the particle, the model of fundamental interactions will not stand together. So it's been really crucial. After that, he decided to start something new, which is fantastic, which is the alpha magnetic spectrometer experiment that is in space rather than on Earth. And he is the leader of that collaboration, which counts 600 people right now all over this place. And I'm sure he's going to say more about that. It costs roughly $1.5 billion. So it's not nothing, to bring us to new heights. I will leave Sam to take the word from now. And I say we are very, very happy to have you here.
No, I have one already.
You already have one.
Good afternoon. I have always wanted to visit the Institute for Advanced Studies. When I was young, I dreamed of visit the Princeton Institute for Advanced Studies, spent some time there, and I never had a chance. So it is really a great honor for Susan and myself to visit place and enjoy talking to you, Song, And I also want to thank Francesco for inviting me. And in addition, it's great to meet you, Matt. And I don't see Claudia, but I enjoy meeting her also. What I would like to do today is to share with you some experience I have in doing experimental physics. So the first accelerator was 1612, where Galileo did his fundamental work on gravity by dropping two objects reaching the ground. And it's very low energy, perhaps that's done one of the most fundamental work. The current accelerator, the largest one, has extreme high energy, and it's to study fundamental building block of nature. Francesco have done enormous amount of work at CERN. So after so many years, we now know elements on the periodic table. Outside has electrons, inside a nucleus, inside the nucleus there are particles, and inside the particle there are quarks. So after 400 years, we realized electrons and quarks are the smallest element of nature, as of now. So let me share with you 5 short stories. The first is measuring the size of electrons. The modern electromagnetic theory by Feynman, Schwinger, Tominaga was made in 1948, required that electrons has no measurable size. The theory agreed well with all experiments. In fact, this is why the 3 received the Nobel Prize. Until a large electron accelerator, CEA, known as Cambridge Electron Accelerator, provided a more sensitive measurement of the size of electrons. The experiment was done by world's leading expert in the field, who had spent many years developing the technology for the experiment. So Cambridge Electron Accelerator was built jointly by Harvard and MIT. It has an accelerator with a circumference 320 meters, and then when the electron bends through the magnet, it emits light about 6 billion electron volt. And because of high energy light, you look into the electron and see if you can see the size. For physicists, it means the photon go to electron-positron pair with the momentum transfer for the recoil nuclei, and you have a delta T in here, and delta T is the order of GeV, so delta T, delta R equal to constant, delta R is 10 to the minus 14 centimeter. But you don't need to know this. You just realize when you measure things, you need to use light to measure. So this was the results done by the Harvard group, and it shows the measurement compared with theory. It is not 1. 1 is the theory of Feynman, Schwinger, Tominaga based on electron at 0 size. And the result clearly disagree with the theory, shows electron has a size of 10 to the minus 14 centimeter. Most importantly, this experiment was independently confirmed by a respected group at Cornell Electron Accelerator. So in the 1960s, most of the physicists were talking about the validity of QED, and that was the main topic. Since those results touch upon the foundations of modern physics, I decided to repeat the experiment with the independent method. At that time, I'd never done an experiment by myself. I knew nothing about electron physics, so I received no support in the United States. In '65, I decided to leave Columbia University and move to the newly built 6 billion electron volt electron accelerator in Hamburg and to redo this experiment. And so this was the detector. The detector is not interesting. Interesting is there's 2 persons working there, and this person later on become vice president of research at Princeton. This was not the best student, but become an industrialist, rather successful one. So after 10 months working in Hamburg with a different method, we observed that our measurement compared with theory is exactly one. Namely, electron has no size. And so that means electron indeed has no measurable size. The radius is less than 10 to the minus 14 centimeters. So my first lesson is do not always accept the result of experts. Those people spend years, 2 independent groups, most important, 2 independent groups. And here I was really a nobody. I managed to challenge that. The second story is what Francesco mentioned, discovery of new kind of quark. By '70s, all the non-elementary particles could be traced to 3 kinds of quarks, U, D, S. You can call it any name you want. And so a pi meson would be this type of quark, a proton would be this type of quark. The question I asked, why only 3 types of quarks? To look for new quarks and the heavier photon, I decided to set up a very sensitive detector. So how sensitive? So I set up a detector to look for new particle compared to known particle 1 in 10 billion. What does 1 in 10 billion mean? During the rainstorm over Copenhagen, there are about 10 million drops per second. And if you try to find 1 drop in a different color, of course, it's somewhat difficult. So the experiment was not popular with the physics community because most physicists believe there are only 3 kinds of quarks. Because 3 kinds of quarks can explain all the known physics phenomena. Experimentalists believe no one can do such experiment. So the experiment was rejected by nearly every accelerator in the laboratory, in the world. So we had this discussion yesterday. Finally, in 1970, the experiment was accepted by the Brookhaven National Laboratory. So when you have a proton go to a nuclear target, you produce many, many particles. The most difficult one to find is the electron-positron pair because the rate experimentally is 1 in 100 million. So to obtain enough electron-positron event, you need 1 trillion protons per second. To reject pi plus minus to 1% level, you need a rejection 1 in 10 billion. And this is why everybody thinks this experiment cannot be done. To do this experiment, first thing you need to do is you modify the accelerator. And so when the accelerator reaches the full energy, you change the orbit, you take all the protons out. Taking all the protons out means no other people can do the experiment. And so you put the proton on your target. The detector is designed to measure the momentum and angle independently, because if you want to look for particle, and the particle mass is momentum times angle. So a good resolution means you measure them independently. So looking from the top, you measure the production angle. Looking from the side, you measure the momentum. So M0, M1, M2 are magnets. C0, CE are velocity measuring devices, measure to accuracy about 1 in 1,000. And these are position detectors. When you have 10 to the 12, 1 trillion particle per second on a target, you produce 1 trillion particles, secondary particles. So in order for your detector to survive this, you need to shield the detector. At first, you use 5 tons of uranium, use 100 tons of lead, and use 10,000 tons of concrete to stop all the other particles. Once this is stopped, you still have neutrons walking in all directions. It's like a nuclear weapon explosion. Finally, you have a lot of neutrons. To stop neutron, the best thing you can do is soap, because soap contains a lot of water. Imagine the difficulty. You go to the US government to ask for 5 tons of soap. And finally, the soap was provided by MIT. And even after that, the radiation in the target area is still 5 Röntgen per hour, a rather deadly radiation. So this is a 2-arm detector, where each length is about 50 meters. And this is when you shield it with 10,000 tons of concrete. So how do you distinguish pi plus, pi minus from electron to a 1 part in 10 billion? When a particle goes through, you use the velocity measuring device known as Cherenkov counter. A pion will interact with the atomic electron, and so an electron will be moved forward. It's a small probability, but in 1 in 10 million, you have to avoid that. So to do this, you put in hydrogen, because hydrogen contains the minimum electron. And you use 2 counters, you separate by magnet, and so the low energy electron is taken out. So these are many of the high resolution, high density radiation resistance detectors, and this was exhibited at Smithsonian Institute in Washington. It's still used today to work in a high intensity radiation area. So with all the detectors, you must assume that they can go bad. They can be dysfunctional. So you have to do calibration. Calibration means what is the response of the detector when you have a known process going in. And so you know pi 0 goes to E plus E minus. And so if you have an E plus going in this direction, you have an E minus measured in this detector. In this way, you have a calibration. So you know how accurate the detector will be. Now, you have a target. If you put a target into many sections, that's 10 sections, and then a genuine signal will come from 1 place. A background will come from 2 places. In this way, you reject the background. So this was the signal in August 1974 at the mass of the electron-positron pair. At this energy, it suddenly goes up. But the rate is extremely low. So how do we know this is a real signal? And the thing to do is the blue one is when we have the magnet with the full strength of field. The red one is when you have a magnet at 90% of the field. When you move the magnetic field lower, the particle, of course, go to a different part of your detector. Yet, the peak is still there. That means it is not due to instrumentation. So the unique property, as Francesco just mentioned, of this detector is the lifetime is 10,000 times longer than other particles. So the significance of this is similar to suddenly discover in a remote region on Earth, a village where people live instead of 100 years, but 1,000,000 years. That means this group of people are somewhat different from you and I. And that means something new has occurred. And also, this particle is bounded by two particles because they transmit to different states, like an electron-positron atom. It means it's a combination of two quarks. So this implies the existence of a new kind of matter made of new kind of quarks. And therefore, the concept of three kind of quarks was wrong. Now we know, once you have break this concept, now people look for more particles. Now we know there are at least 6 kind of quarks, known as U, D, S, C, B, and T. We're now up to now. 100 years from now, how many we have, perhaps it's difficult to estimate. But this is an interesting slide because this shows the production rate of J particle at different laboratories. After we discovered this, measurement in Russia, measurement in Fermilab, measurement at CERN, and shows we have choose the most difficult place to discover it. And the reason is very simple, because most of the other group places think this experiment cannot be done and should not be done. And so my second lesson is it's important to keep faith in yourself, do what you think is right for experimentalists. Yeah. And the third is on gluon. In late 70s, early 80s, the highest energy accelerator in the world for electron-positron is a 14 billion electron volt electron-positron colliding accelerator. And we had a detector in here, which we call MARC-J. The original purpose was to study quantum electrodynamics and to look for electroweak effect, namely electron-positron go to mu plus, mu minus, and that means a virtual intermediate vector boson effect. The existence of this, at that time, it was not discovered yet. The existence of this will cause a priority violation, namely a forward-backward asymmetry. Indeed, the dotted line is if you only have this term, and the green line is to compare, is to fit to the data, show the existence of this term. And that was announced in Physics Today, electroweak interference confirmed. This was 2 or 3 years before Z0. But we found something else, namely the carrier force of carrier of the strong nuclear force, gluons. Gluons bind the quarks together inside the nucleus, so that's why you don't see them. Now, how do you look for this? The first thing you need to realize, at a very low energy, when you have a positron-electron collision, you produce many nuclear particles. They have the shape like 3 jets, and from top view, 2 jets in the side view, or a planar event, many jets and 2 jets. And this rate can be explained without gluons, just quark-quark interaction, standard QQ bar interaction. So the observation of 3-jet or planar event does not require gluons. How gluon was discovered? When you look at the fact of positron-electron collision, produce a quark, antiquark, and gluon. And then with the increased energy of gluon, you have the growth of the 3rd jet. The important thing is when the production rate of the 3-jet agrees with the gluon theory. And with the QQ bar, you do not explain this. And so evidence from Petra adds support for QCD and gluons. So the important thing for this discovery is to observe the rate and shape agree with the QCD. So my 3rd lesson is be prepared for surprises, because when we start experiment, nobody thought about doing that. My 4th, I only have 5 stories, so the talk will be very short. The 4th story is a large international scientific collaboration. The L3 experiment at a 27-kilometer large electron-positron collider. It lasted 20 years with many physicists, many countries. So for those of you who have not been there, this is the border, and this is Switzerland, this is France, this is Geneva Airport, and I think we lived in here. But the idea, it's a very simple one. When you have 100 billion electron volt electron, 100 billion electron volt positron collide, and during the collision, you produce the temperature about 400 billion times the surface of the sun. You can easily imagine that because the temperature of the light bulb is 210 volt, and here you are 100 billion electron volt. That means in the laboratory, in a controlled condition, you produce the very, very beginning of the universe. I already mentioned the world is made out of point-like particles. We found 6 quarks and 3 types of electrons. One called electron, one called mu, one called tau, and its associated neutrinos. So the question is, how many types of electrons are there? Why only 3? Do they have a size at all? Can they be divided into smaller particles? Experimentally, you can ask, how many quarks are there? Why are there only 6? Do they have a size? Can they be divided into smaller particles? So this is the L3 experiment. It's about 6 stories high with many layers of detectors. And basically, the detector principle is very simple. A electron will leave this type of trace, a muon will leave this type of trace, a light will leave this type of trace, nuclear particle leave this type of trace. And this is how you distinguish them. So this is the L3 experiment. And this is the beginning of a very large international collaboration. Originally, there are about 15 countries, and during the process of the experiment, Soviet Union become many more countries. And so we wound up of about 20 countries. So we published 300 papers, and this is the front page of Scientific American, depict the analysis of the events. To me, the simplest thing is the 300 papers can be summarized. There are only 3 types of electrons. Electron we're familiar with, electron from space, 200 times heavier, electron inside the nucleus, 4,000 times heavier, within the given available energy. Yeah. 100 years from now, this will expand. And there are only 6 kind of quarks from occurrent energy. But more important, the electron quarks has no size. Their radius is less than 10 to the minus 17 centimeter. Let me remind you, when I first doing physics, the electron size was 10 to the minus 14. After nearly 3 decades, you reduce 3 order magnitude. It's very curious why you never can find the electron size. Fortunately or unfortunately, more likely unfortunately, all the results agrees with the electroweak interaction of Glashow-Weinberg and Salam to a high accuracy. I think this will make Francesco happy or not happy, hard to say. But for experimentalists, when your data agree with the theory, what you learn is limited. When the data does not agree with theory, you learn much more. So my fourth lesson on large international collaboration, which now has become a trend in many areas of fundamental research. They involve many countries of diverse social and economic origins and often last for decades. To have a successful international collaboration, you need to choose an important topic so people are interested in what you're doing. And giving recognition to young scientists. It's almost 20 years now. I normally don't give talks, and the talks in our collaboration are always given to young scientists. And also, it's very important to respect the diversity of your collaborators. And to me, the most important thing, do not compromise on instrumentation. Because when you compromise on instrumentation, you will not do the best experiment. And you try to build the best detector as possible. My last story is the alpha magnetic spectrometer on the International Space Station. It is like my previous experiment, except it's somewhat smaller. The idea can be simply visualized. There are 2 kinds of cosmic ray traveling through space. Neutral cosmic ray, light rays and neutrinos can be measured with satellites and large ground-based and underground detectors. And beside neutral cosmic ray, there are charged cosmic ray. Because it has charge, it must have a mass. Because it has a mass, the Earth's atmosphere, which is equivalent to 10 meters of water, and therefore absorb charged cosmic rays. So the property of charged cosmic ray cannot be measured on the ground, because it goes through 10 meters of water, it's absorbed. AMS on the space station is a large acceptance, long duration magnetic spectrometer directly measure the original property of charged cosmic rays. In other words, over the last 100 years, much of the work has been done on neutral cosmic ray, and this is the first time people try to do precision charged cosmic rays. So this is a detector, 5 meter by 4 meter by 3 meter. It just fit in to a space shuttle. It weighs 7.5 tons. It is a trillion electron volt precision magnetic devices. Particles and nuclei are defined by their charge, their position on the periodic table, their energy, and something called rigidity. Rigidity means momentum per unit charge. Charge is a location on the periodic table. For proton, electron, positron is 1, for helium is 2, for lithium is 3. The first detector gives out a signal when an electron positron goes through, known as transition radiation detector. There are 9 layers of silicon detectors, measure the charge, and measure its bending. And then there's an electromagnetic calorimeter, measure energy of electron positons. There are two banks of time-of-flight counter, measure energy and charge. Magnet distinguish positive from negative. Rain image Cherenkov counter measure nuclear charge and energy. Therefore, charge and energy are measured independently by many detectors. Now, why people have not put a magnet in space? It's because of magnetic compass effect. If you put a magnet in space, one end will point to north, another end will point to the south, and so your space station will lose control. Finally, we figure out a way to design a magnet so that it arranged with two closed loops, the magnetic field. So looking from outside, this cancels this, this cancels this, this cancels this, and this cancels this. So you do not see the field. All the field are inside. Simple little idea, took 40 years to find out. Because nobody has ever put a magnet in space, so we actually drilled 10 magnets. 7 magnets to understand how you calculate the field, whether the field leaks out, and whether it rotates. Then we build 3 full-size magnets. One, you do vibration and acceleration to make sure it doesn't fall apart. And second, you try to destroy it and try to understand at what condition the magnet will fall apart. Because the magnet contains 4,000 pieces, and the force is 4 tons between them. And if one flies out, it will destroy the space shuttle, and that will not be very good. And third is a fly magnet. So it is a collaboration with many, many countries. Most important, Italy, Switzerland, Spain, Portugal, France, Netherlands, Germany, Russia, Finland, China, Taiwan, Brazil, and Turkey, Mexico, and United States. So I want to mention to you, it's a very large experiment. No one in the collaboration had ever worked before on space experiment. So experience we do not have. In fact, I received such a cartoon which said, it's time we face reality, my friend. We're not exactly rocket scientists. None of us are. And it is not a cheap experiment. And I received such a cartoon that we have just decided launching money directly into space was cheaper. And you cannot imagine how many discussions, how many objections people have. And those are the 2 reasons I mentioned. Some people said, well, these people have never done experiment in space. And others said, well, it's so expensive. Finally, to send AMS to space, the United States Senate and House of Representatives passed a unanimous resolution, HR 6063 in 2008, requesting the US government to provide a shuttle to deliver AMS to the space station. So it required a congressional resolution to send us to space. So this is the night before the shuttle launch. And that night, I received an invitation from the astronaut, it's the captain, the total 6 astronauts, to have a dinner with them the night before the flight. And they were very relaxed because they were under quarantine for 2 weeks. And in order to have a dinner with them, I had first to have a physical checkup to make sure I don't bring germs to them. And the dinner was very good, almost the same as what we had last night. But these people were very relaxed, and I, of course, was not. Because I realized after this dinner, the AMS will be in space, I will not be able to see it again. And so you sent to space the next day at 8:56 a.m. The whole system weighs 2,008 tons. And AMS weight is 7.5 tons. So this is AMS. It goes to a geosynchronized satellite, go to White Sands, New Mexico, and go to Payload Operation Control Center at CERN. In there, there's a screen, and shows on the 27th of August, we had 105 billion cosmic rays, up to trillion electron volts. So let me share with you some of the physics. And the physics goals include the search for origin of dark matter. We know about 90% of the matter in the universe is not observable. Because you cannot see it, you call it dark matter. The galaxy seen by telescope is something we're familiar with. And if you could see dark matter in the galaxy may look like this. There are many theories that dark matter could be a particle, could be a different kind of particles, but no matter what kind, collision of dark matter produce energy. Energy can produce positrons and antiprotons, because energy changes into matter. And so this collision will produce positrons, antiprotons, will be detected by AMS. In addition to this, there are the traditional method of cosmic rays interact with other cosmic rays, interstellar medium, just other cosmic rays, will produce positrons and antiprotons, and this will also be detected by AMS. So this additional positrons and antiproton from dark matter can be easily measured by us. So this is one of the model, shows the annihilation of dark matter produce additional positrons, which are characterized by a very sharp drop-off of this positron spectrum, and that is because the finite energy of the original dark matter mass, and so you cannot produce infinite energy positrons. And so the spectrum you expect from the addition of collision of cosmic ray and collision of dark matter. So you will expect such a spectrum with dark matter mass of 1 trillion electron volt. And this is all data today. The data is very, very close to this model. And with more data, we need to make this more accurate, see how quickly it drops off. I was quite surprised. The data follow this model exactly. Because when we start measurement, we couldn't care less about this model, and yet this model seemed to agree with data. There are, of course, many other explanations. There always are. And some says from dark matter, some says from astrophysics sources, and some says from collisions. One of the model says, no, this axis can come from pulsars. By continued measurement to the lifetime of space station, if it is pulsar, we will see this curve. If it is dark matter, we will see this curve. So by the end of space station, we shall hopefully resolve this issue. Pulsars does not, where it produces positron electrons, it does not produce antiprotons because the mass of antiproton is so large. And so when you measure antiproton to proton ratio as function of its energy or rigidity, and this is our measurement, is also in good agreement with dark matter model. And this is in disagreement with the collision of cosmic ray with the interstellar medium. So let me share with you some very interesting knowledge of elementary particle in space. There are hundreds of different kinds of elementary particles, muons, pion, K, lambda, and so forth. Only 4 of them, electron, proton, positron, antiproton, have infinite lifetime. So they travel in the cosmos forever. The electrons and positons has much smaller mass than proton and antiproton, so they lose much more energy in galactic magnetic field. That's how synchrotron radiation come about. First, let me on measurement of protons. Protons are the most abundant cosmic rays. Before MS, there has been many measurements of proton, and these are the measurement, and typical error is about 50% to very high energy. In cosmic ray model, proton spectrum before AMS was assumed to be a single power law, limited flux is equal to a constant times energy to the gamma power, where gamma is minus 2.7. This was the knowledge before AMS. This is the measurement of AMS to an accuracy about 1%. This measurement is in agreement with single power law up to this point. And after this point, you have unexpected excess, and it grows up very slowly. And so it does not agree with the current theory. Now, proton has much larger mass than electron, and therefore the loose energy, proton lose energy much slower than electrons. Electron lose energy much faster because it's smaller mass. This is what you expect, nothing special. What is special is the spectrum of antiproton and proton. They're exactly same energy dependent. This is indeed very strange, because antiproton is thought to be from proton collision with other proton produce antiproton. And if that indeed is the case, there is energy dependence, and this should be different. Yet they are exactly the same. Most difficult to understand is that the positron spectrum, with positron at the same mass as the electron, so they lose the energy, they should lose the energy in the same way that the positron spectrum, 2 trillion electron volts, is different from the electron. This is really one of the great puzzles we have, why electron and positron behave so differently in space. To very, very high energy. Even more curious is the rate of loss of energy of positron is same as antiproton and proton, even though the mass of positron is 2,000 times smaller. And this is not low energy, this is go to trillion electron volt. So for elementary particles, positron, antiproton, proton, lost energy the same way. The electron behaves normally, lose energy much faster. It's a great mystery. So far, I have not heard any explanation. Now, besides positron electrons, once you are in space, you can measure periodic table. Periodic table we know on Earth. The question is, does it exist in space? Indeed, they exist in space, and we have 7 instruments to measure, to identify nuclear elements. So there are 2 kinds of cosmic rays. One is primary cosmic ray, proton, helium, carbon, oxygen. Primary cosmic ray comes from its source, travels through space without interaction, and is detected by MS. Primary cosmic ray carry information about the original spectrum and how it's propagated. So, first primary cosmic ray is helium. And this is based on 90 million cosmic rays. So this spectrum, it's like proton, does not agree with traditional assumption, and up to certain energy, you have unexpected, unexplained increase. Now, if you look at the ratio of proton over helium, this is the measurement of AMS near Earth and therefore inside the solar system. In 1962, Mr. Edstone of Caltech sent out 2 satellites, and after 50 years, these 2 satellites has left the solar system. And it's a very small satellite, use nuclear power, therefore still work, and they measure very low energy proton over helium. And they found this ratio. So this ratio outside the solar system and inside the solar system are the same. Shows this ratio is independent of solar activities. And this measurement of carbon, primary cosmic ray, this is measurement of oxygen. This measurement turned out to be quite difficult, and therefore there are no other measurement of oxygen. What does this tell you? This tells you an incredible thing, and that is the energy dependence or rigidity dependence of helium. It's a black line, carbon, the green one, oxygen, the red one, they're exactly the same. So above 60 billion electron volts, the flux are identical energy dependence. There are totally different elements on the periodic table, but the energy dependence is exactly the same. No one can explain that. Besides the primary cosmic ray, there are the secondary cosmic ray. And they come from primary cosmic ray, interact with other cosmic ray, produce lithium, beryllium, boron, and so forth. So study secondary cosmic ray carries information about propagation of the primary cosmic ray, propagation of secondary cosmic ray, and the interstellar media. So this is the measurement of lithium compared with previous measurement, and this is the theoretical prediction. And so they are quite a distance away from each other. So this is lithium, and this is beryllium. This is all data, and this is theoretical prediction. And this is boron. This is the current measurement. Does not agree with the previous measurement. Does not agree with theoretical prediction. What we can learn from beryllium to boron ratio is the age of cosmic rays. Beryllium is secondary cosmic ray. It travels to space. It has a half-life of 1.5 million years. Then it decays to boron. So this ratio will rise with time due to relativistic time dilation. And because of this rise, you can find out the age of cosmic ray in the galaxy. So this is based on 3 million events. Indeed, you can see from low energy to high energy, the ratio rises. Ratio rises means at this moment, you determine the cosmic ray exists in the galaxy 50 plus minus 5 million years. And eventually we will get to 2 million years. So you know how long cosmic ray wandering around in space. Now let me come on the issue of antimatter. The great British physicist Paul Dirac, who received the Nobel Prize in 1933 on the theory of electrons and positons. He noticed the equation of motion of relativity and quantum theory, the mass term always appear to be squared. That means it can be m times m or minus m times minus m. Most people will ignore it, but he asked, what is minus m? Leads to the theory of antimatter. This means for a true genius, getting a Nobel Prize is quite easy. Indeed, Carl Anderson in 1936 received a Nobel Prize for the discovery of positively charged electron, known as positon. So the question then is the following. If the universe comes from a Big Bang, then at the very beginning, the matter and antimatter should be equal amount. So the question now, the universe is 15 billion years old, and we have this institute, we have MIT. The question is, where is the universe, if it exists at all, made out of antimatter? Heavy antimatter, such as antihelium, has never been observed in cosmic rays. Therefore, one of the main physics research topics in the last half a century is search for explanation for the absence of antimatter, known as search for baryogenesis, namely only positive matter. And this is the famous Atlas experiment, which you are very much involved. And despite of many outstanding experimental efforts over the last half a century, no evidence for strong symmetry breaking has been found. So the observation of a single antihelium event is of great importance, because everybody thought it cannot exist. Today, we have observed few events with charge -2 and with a mass like helium-3 at a rate of 1 antihelium per 100 million helium. That is a very small number, 1 over 100 million, 100 million. So at a signal to background ratio of 1 in 10 to the 9, because you want a 10% background, detailed understanding of the instrument is required. But the detector verification is very difficult because we have a permanent magnet. You cannot change the magnetic field to move the particle to a different part. Also, the rate is about 1 per year. So you can do computer simulation. We have spent 2.2 million CPU days, 10 times more events than the helium data. We have not found a reason to explain this. We have not found any mistake. But then the question is, how do you know your simulation is accurate to 1 in a billion? It's a rather difficult thing. Nevertheless, the few events have the mass and charge like helium-3. Their existence, of course, has fundamental implications in physics. So we are now developing technology, try to ensure the event is not from detector effect. So the result of this experiment today are unexpected and began to unlocking the secrets of cosmos. And we need to work closely with the theoretical community to develop a comprehensive model to explain our observations. Because so far, there's no theory can explain all this phenomena we have seen. And in January this year, there was American Physical Society meeting, and there's a conclusion slide by Professor Igor Mostelenko of Stanford, and shows this is a theory. This is a famous Russian painting. This is the theories and the new AMS data. So let me finally share with you my understanding of some of the important discoveries in physics. When proton synchrotron was built in 1960s, the original purpose is to study pion-nucleon interaction to understand nuclear force. What was discovered was neutral current leading to the discovery of Z and W. Later on, Brookhaven built the same accelerator, also studied pion-nuclear interaction, leading to however, the discovery with instrument was two kinds of neutrino, time reversal violation, the J particle. When Fermilab was built, was to study neutrino physics, what was discovered was the fifth and sixth core. When Stanford electron positron was built, opinions from a committee from U.S. National Academy of Sciences was to say you can study electron-proton scattering, measure the size of the electron. What was discovered was partons, the fourth type of quark, third type of electrons. The large electron-positron collider, Petra, built in Hamburg, original purpose was to look for the sixth quark. What was discovered was gluons. The large underground experiment in Japan originally was to look for the lifetime of proton. What was discovered was neutrino oscillating to each other because of its mass. Hubble telescope, its original purpose is to do galactic survey. Among its discoveries, the dark energy, the flat curvature of the universe. So I have been trying to explain to you, AMS on the space station will look for dark matter, antimatter, many other things. What ultimately we will see, nobody will know. And that's because exploring a new territory with a precision instrument is the key to discovery. Up to now, whatever we have seen on AMS cannot really be explained by current theory. So for me, the most important thing for physicists is to be curious, enjoy what you're doing, and work hard to get your goal. So, thank you.
So thank you, Sam, for a very inspiring lecture, brilliantly inspiring lecture with a lot of things to think about. Now we have some time for questions.
If you want to, I think it takes 5 minutes to show you a video taken by NASA.
Please.
What you have to do to get to space. But maybe it's possible to lower this.
I also want to say, while Sam is preparing the video, after that there will be a section, so you're invited to some live so hope you enjoy.
This is a building AMS. It takes 16 years to build. Space Agency. Return to CERN to test in the testing. Sent to Kennedy Space Center. This is in Kennedy Space Center. This is in the Space Center.
Liftoff for the final launch of Endeavour, expanding our knowledge, expanding our lives in space.
Houston, Endeavour, roll program. Roger, roll, Endeavour.
Houston is now controlling. Endeavour beginning standing by for separation of the solid rocket boosters.
After 123 seconds, the solid rocket is used, so it's ejected. So after
And
8
main
minutes,
engine cutoff has been confirmed.
the liquid tank is ejected. You use
Flight
explosives
Dynamics
here to
reporting a
eject it.
nominal main engine cutoff. And separation from the external tank. Endeavour's Commander Mark Kelly now firing the thruster jets to position the orbiter for photography of the external tank.
We did see a nominal MECO. Ohms 1 is not required. Copy, nominal MECO.
By the way, I don't understand what they're saying.
It was very, very nice. They appreciate everything you did for them and wish you all the best of luck in your flight.
We'll be assisting Mark Kelly, the commander, with the rendezvous and docking activities today.
So this space station, space shuttle, approaching the space station.
Copy, tally ho.
Initiating RPM on my mark. 3, 2, 1, mark.
And the R-bar pitch maneuver is underway beginning at 4:15 a.m. Central Time.
Endeavour Houston on the big loop. We're following you in docking mech power up, and you have a go for docking.
Endeavour copies on the big loop. Go for docking.
This shuttle only carries AMS. Now they dock with the space station. Not exactly easy because both traveling at very high speed.
Capture is confirmed.
Incoming.
Hello, Dima. Welcome aboard the station. Hey, you guys wore coordinating shirts. We didn't do that. That's okay. Hello. How's it going? How are you? Good. Nice to see you here. Nice to see you. Welcome. Come on. Good seeing you. Hello, everybody. Hello, how you doing? Nice to see you guys.
Going out. So this is the AMS. Use the space shuttle arm to take it off. By then, you have no more weight because there's no gravity anymore. So you use this arm to pick us out. And give to the space station arm. This is space station arm to connect them. Traveling at 23,000 kilometers per hour. Take the 6 astronauts in the
And a good capture is confirmed. The station robotic arm now is locked onto the grapple pin of the alpha magnetic spectrometer, occurring as Endeavour and the International Space Station track to the southwest of the Canary Islands.
I just want to say a few words to you and to your crew. And thank you very much for the great ride and safe delivery of AMS to the station. Your support and fantastic work has taken us one step closer to realizing the science potential of AMS.
Well, thank you, Sam. I was just looking out the window of the orbiter, and AMS looks absolutely fantastic on the truss. I know you guys are really excited, and you're probably getting data and looking at it already. I'm going to turn the mic over to Box and Paz and let them make a couple comments about how that all went. We have been working for this day a long time, and me and Drew Feustel this morning very early start to prepare. Everything went very smoothly. The robotic arm performed perfectly, and within the time that we were given, we were ready to hand it off to Box and Paz.
So the shuttle returned to Earth 2nd of June at 2 a.m. So that's it. Thank you.
I guess there is only one word for that, cool. That's very, very cool. So, any questions? Here we go.
Thank you very much for your great talk. My question was not related to physics.
You please speak louder.
My question is not related to physics. I would like to know some of your personal feelings that when you get to know in 1976 that you were awarded Nobel Prize, like what were you doing at that moment and how did you feel that you get to know that you won Nobel Prize? And second question is, what motivated you to do research?
If there are too many questions, I will forget how to answer them. So I received a phone call when my wife and I were in the lab. October 18th, about mid in the morning, near noon, there was a call from the Royal British Academy of Sciences and informed me I received the Nobel Prize. I was quite surprised because normally from your work to recognize you, normally it's 10 years, 20 years, sometimes more than 20 years. In my time was less than 2 years. So I think probably they let the excitement overcrowded their judgment.
Thank you very much.
So, another question?
Yeah, I was just wondering when you were making the experiment for looking for the fourth quark, did you know what you were looking for, and did you find it where you find it? Or were you expected to find it?
No. Nobody believed there would be additional quark because 3 quark at that time was the standard model at that time. Quark model was proposed by Murray Gell-Mann, and for which he received the Nobel Prize. And I was just curious why there are only 3. And,
so the signal
I had a unanimous objection from the physics community.
Yeah.
Because people said,
but it was in accordance with the theory when you found it. It was in accordance with the theory when you found it.
No. Later on, Professor Mayani and Glashow and say they predicted before, but before that, I did not hear anything. It is important for experimental physicists to know theory, but perhaps it's even more important to understand the limit. Yes, please.
For the energy dependence of the...
You need to speak louder and
for
keep
the
a
energy
distance.
dependence of the proton, the electron, the positron, and the antiproton, is it only the relative energy dependence, or is it also the total flux that seems to be the same? Because I was curious about the units on the axis.
Oh, it's the total flux. Both the behavior of the total flux and energy. It's very difficult to imagine. Electrons and positons behave differently. Okay. Exactly the same. Proton, antiproton, exactly the same. Electron, positron are different.
And the positron matches the protons as well,
Yes.
also in flux?
Yeah. Difficult to imagine. Very difficult to imagine.
A question? Well, if not, you will have the time outside to speak with Sam, because there's, as I said, a little reception. And also, I would really like to thank again Samuel for a fantastic lecture and for giving us the opportunity to meet him, give you the opportunity also to meet him and to enjoy his presence. Thank you.
Thank you.
Something for you to remember, something for you to take together with
Wise choice. Thank you. And again, now please join us at the reception. I'm sure you're going to have fun. And thanks for coming in front of me. We also appreciate it.